sustainable way of designing and developing products in terms of developing environmentally friendlier products, process, and so on. So in this context, my lecture, I'll be focusing on these two important manufacturing systems, like smart and sustainable manufacturing systems, and the connect between these two systems. Fine. This will be my presentation overview. Let me first focus on the smart manufacturing, the concepts, the methods, and then on sustainable manufacturing, and then we shall discuss about the integration and other research perspectives as well. Fine. So I'm now in slide 3, origin of smart manufacturing. Is my slide 3 visible? Attendees, is my slide 3, origin of smart manufacturing, is it visible to all? Fine. Okay, so let me just go ahead with the discussion. As we all are aware, now we are into the 4th industrial revolution, and we have crossed like 3 industrial revolutions. The first version is about like mechanization, wherein we focus on like mechanical and steam power, we focused. And then the second revolution, wherein we focused on like automated lines, assembly lines, wherein we utilized the electrical power. And in the third industrial revolution, we focused on developing and utilizing electronics and information technology in order to move ahead with the with the focus of a digital factory. And in the present 4th industrial revolution, our focus is to make the manufacturing system smarter. And the same term in the context of German industries is it's referred as like Industry 4.0. Though they have like synchronous meaning, but there are some slight differences in terms of like methods and the convergence towards the smart factory. That also we shall discuss in due course. So in the 4th industrial revolution, it's more interesting, and it has brought like a lot of challenges, wherein it has a range of interconnected automated systems with the fusion of the physical, digital, and biological scenarios. And here we go to the advanced levels of automation in terms of utilizing like computing and interconnection technologies, and also the role of... Sir, are you mentioning something?
Yes, sir. Actually, it is in slide 2, sir.
So that's why I asked. Earlier also I asked. When I moved to slide 3, I asked. I didn't get any response.
Oh, it is in slide 2, sir.
So now I am in slide 3. Is my slide origin of smart manufacturing visible?
No, sir. It is in slide 2.
But I have more. That means you could see only content slide. Now I am in origin of. Now I am in origin of smart manufacturing.
No, sir. It is in content slide.
But I don't think my connectivity is also fine. Okay. How about others? Other attendees?
Same, sir. We could see only content.
Okay. Then means I can unshare and share again. Just a moment. I'm sharing again. Is it visible now, like origin of smart manufacturing?
Yes, sir. Is it visible, sir?
It's fine now? Okay, fine. Yeah. Okay, let me just continue. Okay, as I mentioned, like Industry 4.0, the term originated from German industries, and in the context of US, it's referred by the term smart manufacturing, wherein the focus is to develop a smart factory, wherein the 4th industrial revolution has brought a lot of challenges in terms of developing a wide range of interconnected automated systems, which are characterized with the fusion of physical, digital, and biological scenarios. And that has bring about like a lot of challenges in terms of designing and deploying the systems for smart factories. So in this scenario of manufacturing, the role of computing technologies and the interconnection devices are also essential. Also, they have to be augmented by automated material handling systems, like the automated storage and retrieval systems on automated guided vehicles, which are used in the context of flexible manufacturing. Also, they have certain significance and in terms of coordination among various entities of manufacturing.
ನಾನು ಅದ್ರ ಬಗ್ಗೆ
ಮೆಂಟ್ಲ್ ಆಗ್ಬಿಡ್ಬೇಕು ಆ ತರ ಕ್ವಶನ್ಸ್ ಕೊಡೋದೇ ಇಲ್ಲ ಕೊಡಲ್ಲ
And
ಕ್ವಶನ್ಸ್
the
ಓದಿ
need for,
ಕೀ ಮಲ್ಟಿಪಲ್ ಆನ್ಸರ್ಸ್ ನಾವು ಅನಲೈಸ್ ಮಾಡೋಷ್ಟಕ್ಕೆ
so there is an interruption.
2 ನಿಮಿಷ ಎದುರೋಗಿರುತ್ತೆ.
ಸಖತ್ ಟಫ್ ಕಣ ನೀಟ್.
ಬಟ್
Coordinators, there are some interruption. Okay, in the context of like smart manufacturing, when we explore the need for smart manufacturing, we need to deal with the challenges in terms of like complexity, customization, globalization, and to deal with customers' expectations. And the focus is on digitalization of manufacturing. And the systems rely on advanced modeling, optimization, and simulation modules with the greater horizontal connectivity and also interoperability between the systems. And the interaction in terms of like materials, product, process phenomenon is also gaining much importance. So the three building blocks of like smart manufacturing we look about, it includes like information technology and like the human ingenuity or the human intellectual ability, which is very essential. So as we understood, the manufacturing scenario has undergone changes, and there are several incremental changes in the operational practices. So the manufacturing complexity keeps increasing, and accordingly we need to work on with transformative approaches in the context of manufacturing, which needs the utilization of new data modules, knowledge-based systems, and beyond in IT technologies to like IoT and other IoE level of technologies are also very essential. So here the manufacturing scenario faces a lot of uncertainties, and also the dynamism comes in varied perspectives in terms of like cost, design, quality, quantity, and delivery measures. The prediction of the manufacturing system is also very crucial, and the need for prediction models is also very essential. So as we could see in the picture, the transition of the manufacturing systems, starting from the version 1 where the focus is on like mechanization, and the second is about like electrification, and the third is about like utilization of electronics and information technology, and to the robotic systems, also like 3D printing technology, and now the focus is on like the fourth industrial revolution, which is based on the cyber physical systems, ultimately to develop smart factory. And also there are like further revolutions in due course, like the fifth and sixth also will be phasing progressively. As these terminologies like Industry 4.1, smart manufacturing, they have certain synchronous synonyms. The vision is to develop a smart factory wherein ultimately the cyber physical systems, which is CPS, is the base for the smart factory. It tries to synchronize the physical and virtual scenarios. Thereby, this needs the support of the sensors, machine learning modules, AI tools, and accordingly the system integration and so on. That helps us in taking ahead with the vision for the futuristic factory. As I mentioned, the cyber physical systems is the base, which has like 3 C's, which are very essential, like communication, computation, and control. So ultimately, the CPS is the base for the smart factory, wherein we try to collaborate the computational elements which can control the physical entities. And basically, the engineering task are being monitored continuously, and they are coordinated, and further they are controlled and integrated through the computing and communication core. This will try to enhance the capabilities of the physical systems by means of integrating the computing and communication entities with the physical process. Ultimately, it helps to develop the digital twin. As we could see, the factory, which is based on the third version of Industrial Revolution, where the workstations are mostly like rigid and they do have like limited flexibility, and we do have certain robotic systems. They do autonomously certain tasks, and the kind of reconfigurability or the changeover seems to be very less in the context of such systems. Where in the present factories, we could see they are totally interconnected and they are interoperable, and they do have modularity, and with the workstations totally they are reconfigurable, and we do have the robots which are collaborative in nature, and they could do coordinatively with the machines and the human workforce, and that makes that enhances the capabilities of the system to become highly responsive to the manufacturing challenges. So some of the design principles, if you go through for like a smart system, starting from interoperability, wherein which is the ability of CPS, the human workforce in the smart factories, thereby it establishes the connectivity and communication through IoT and iOS. And virtualization, it tries to create a virtual scenario of the smart factory by linking the sensor data with the plant and the simulation modules. And the third is about like decentralization, which is CPS ability within the smart factories which can facilitate autonomous decisions. The fourth is about like real-time capability, deals with the capability to collect and analyze data and provide insights very faster. And the service aspect is also gaining much importance in the modern manufacturing scenario. And the modularity is about how the smart factories can flexibly adapt for the changing requirements of the individual modules. So these design principles are very essential, and they govern the execution of a smart factory. So now we could see the enterprise, the digital enterprise, which connects the physical and the digital scenario. And there are like a lot of engineering functions starting from product design, production planning, production engineering, production and services. And we do have like technologies in the system, starting from the simulation modules, product lifecycle management modules, and integrated automation, which can, and also lifecycle management tools, which can help in the coordination and the interlinking of various functions in the context of like the digital factory. And this is more interesting to look about the skills which are very relevant in the context of the smart manufacturing, which is given on the left side, and the right is about like the prior versions of the revolution based on an Industry 3.0 scenario. But in now, the present scenario, the higher levels of creative and innovative thoughts is very, very essential. And also the cognitive skills and the cognitive ability is also gaining much importance, wherein for a problem, the solutions, not only a single solution, but multiple solutions have to be generated, and they have to be simultaneously validated, and how we could converge towards the best solution. So that is possible with the cognitive capability of the human workforce. And it has to be supported with like emotional intelligence and other decision-making skills as well. So these skill sets are very, very essential in the context of a smart factory. Okay. So before I proceed with the technologies discussion, are there any queries at this stage from the attendees? You may feel free to ask any questions. You can post in the chat box, and you can internally, I can break and I can ask, clarify your queries. Are there any clarifications till this stage from attendees? Feel free to ask any questions. Are there any questions at this stage for me? Coordinators, are there any queries in the chat box as of now? Someone could respond.
No, sir. No, sir. No queries in the chat box.
Okay, so you may feel free to attendees may feel free to post the queries, and internally I can break and I can respond to the queries. Okay, let me just proceed with the technologies governing the smart factory. So there are like, as per the literature and the industry reports, 7 basic technologies they help in the execution of a smart factory. Let us go one by one. The first is about like CPS, where we had the initial discussion on the CPS, where this is the base. Like in the third revolution system, if you see, IT was the base, information technology. But now cyber physical system, CPS was the base. And it helps us in terms of coordination, in terms of developing the collaborating computational elements which can control the physical entities. And it facilitates data collection, data analysis, and it ensures the transparency across various manufacturing operations. This is nothing but a concept map of CPS, where we could see there are like several modules, starting from like scalability modules, design module, design tools, and we do have like scalability modules, validation and verification modules, feedback modules, sensing and actuation modules, and the applications in diversified domains. This gives a complete picture of how a CPS is being developed and how it has to be deployed in the context of a smart factory. The second is about like data analytics. So this data analytics and data analysis we have been doing for a longer time and a longer perspective. If you see, the role of data analytics is very essential, as now the scenario is that none of the problems they do not occur again. That's the challenge. The problem will be unique. And another interesting aspect is that none of the solutions which are applied for the earlier problems or the prior problems cannot be applied to this new problem. That means the solutions have to be very unique. So this is the context where the role of data analytics tools comes in a big way. They help us in the manufacturing. So from data, we are moving towards like a big data, like where variety and volume of data are huge. And we need to have like advanced analytic tools to help in solving the problem and bring about the solution for the problem. The decisions have to be very robust and they have to be smarter. So that's very important. So the role of data analytics tools in terms of like AI also helps in such perspectives, including like machine learning and deep learning modules. They help us in a big way. Third is about like system integration, where both horizontal and vertical integration, both are very essential. So here, from a vertical perspective, we need to focus on the in-house functions, various functions starting from like marketing, design, manufacturing, sales, and other further functions are interconnected and how they are very essential. And also in a horizontal perspective, we need to explore that how we need to try to have the partnerships with other organizations, the collaboration with other organizations. Thereby, we shall try to take ahead with the perspective of the various functions in terms of manufacturing, like strategic, tactical, and operational functions. And also the role of horizontal and vertical integration is very essential. And it has to be supported with lifecycle management tools, Internet of Things, Internet of Services, and so on. And we need to take ahead the entities, various entities, the in-house coordination, in-house teams, and also like external teams, and also like external collaborators, the collaborating teams, and how in a synchronous way this systems and technology integration, they help us in taking ahead with the goals of a smart factory. That's more interesting to observe. And the fourth technology is about like additive manufacturing, where there had been a greater emphasis on this approach of manufacturing, wherein we try to add material layer by layer and try to create the component of the product. The technology had been brought in initially to support only the prototyping activity of manufacturing by the term rapid prototyping, where this layer by layer material addition helps in developing a prototype. Thereby, the product development could be expedited. That is what the context. Later, the same layered manufacturing technology had been expanded for tool making in terms of developing production tooling, and next it had been expanded for manufacturing, like the digital or the rapid manufacture of end-use parts, which can work in the field conditions. And now all these terminologies have been unified as per ISO and ISO standard, and they have been come up with the term additive manufacturing, wherein we try to add the material layer by layer, and we try to get the prototype of the component or the end-use product. And there are like diverse technologies in this. Starting from an extrusion process, we do have polymerization, sheath lamination, powder bed fusion, direct energy deposition, metal jetting, binder jetting, and so on. Like several technologies are there, and several advanced technologies have come to support thing, starting from a three-dimensional way of doing additive manufacturing. And now we are moving further towards like four-dimensional additive manufacturing, wherein we try to utilize like smart materials, shape memory materials, and shape memory alloys, and accordingly we try to make the components, and the components on their own they get assembled. So there is no need for like manual assembly, like materials, smart materials, and shape memory alloys. The components they help in taking ahead with configuring the assembly over the period of time, and the time was the fourth parameter. And it's a lot more interesting to see this additive manufacturing has taken a greater lead in manufacturing, where it can be explored as a replacement for many of the traditional manufacturing methods and approaches and the systems. And it is a lot more interesting because it can help us in developing like the complex structures, the lightweight geometries, and the lattice structures, and so on. Because now there had been a greater emphasis in terms of like automotive and aerospace components industries, including like defense components industries, where they need to work on with like lightweight structures, lightweight geometries, and weight reduction is very, very essential. And the role of optimization methods, they help us in a big way. So such perspectives, they bring us a new dimension for manufacturing. And that's how this additive manufacturing has taken. Another interesting aspect is that this additive way of manufacturing is applicable for all engineering disciplines. And it provides an interdisciplinary focus, an interdisciplinary sense of working like all engineering disciplines together in a lot of interdisciplinary projects. They help us. So applications, we could say like almost in all sectors, they have applications for additive manufacturing. And this is having a greater role in this smart manufacturing as we try to develop the systems which are additive and which helps us in layered fabrication, and ultimately try to develop the smarter way of designing and manufacturing the products. Okay. Next comes the role of Internet of Things and Industrial Internet of Things, wherein these IoT and industrial IoT, they help us, and the applications are like in different sectors. And we could see the concept view of an industrial IoT system, wherein we do have the machine tools, we do have these robots, we do have the communication networking protocols, sensors and actuating modules. So these entities have to be coordinated, and accordingly the IoT and industrial IoT, they help us in a big way in terms of like remote monitoring and remote diagnosis, and also like troubleshooting, like in many of the maintenance and condition monitoring applications. They help us in a big way. Next comes the role of like AR, augmented reality, and further we do have VR, virtual reality system. So these AR systems, they provide interactive experience wherein the objects that reside in the real world are totally improved by computer generated information. And these smartphone, these AR technologies, they can be incorporated into the smartphone based applications. They provide something like an interactive and experience for the user. We could see the perspective in this picture, wherein if I'm very new to the working environment, I need to have an understanding on the various maintenance aspects, or the kind of the breakdowns or some interruptions which have happened in the machine tool. The complete history will be available through an AR-based system. And also the manuals, no longer we don't use the manual way of accessing the manuals, but through this digital approaches. And also like this complete maintenance history, and also the various catalogs and the standards, everything could be interfaced to an AR-based system. They provide highly interactive experience for the workforce to take ahead with the deployment. Next comes the role of virtual reality systems, VR systems. They again help us in a big way in providing a very safer way of understanding the systems. Say for example, to that of a gas turbine industry, or maybe like a power plant industry, and have an equipment in the working in the field condition for which the environment is hazardous for us to proceed. So in such situations, through an VR-based device, we'll be able to have a complete experience of how the machine tools works, and the complete the working mechanism could be captured through a VR-based system. So again, it's very essential, and they help us in a big way. These are the various technologies They help us in developing smart manufacturing systems based on Industry 4.0 principles, and also the robotic systems. So mostly we do have like collaborative type robots, the cobots, which are very essential, and they do the task jointly with the interaction of the human workforce and also with the machines. They help us in a big way and take ahead with the industrial deployment. The role of the protocols, the communication networking protocols are very, very essential in the context of a smarter system, where no longer the traditional networking and communication protocols are not sufficient, but they have to be augmented, elevated to that of smart protocols, which starts from the IEEE based protocols, Zigbee, Z-Wave, and ISA, then NFC, Bluetooth, and of course with RFID and MQTT, and a lot of protocols. They help us in execution of the architecture of a smart factory. They have a very bigger role in terms of taking ahead with the application, with the deployment of the smart manufacturing architecture. Next, having discussed on these protocols, next comes the role of the applications in the context of smart systems, wherein this data tracking based on manufacturing IoT is also very essential. With an RFID based system, we'll be able to track the parts, and also it can help us in understanding the inventory related information. They help us in a lot of the information pertaining to the customers, suppliers, product quality, and production process, and logistics data, and so on. So this IoT, they enable the predictive analytics, which is very essential in the context of the automotive systems, whereby we do have the algorithms which can analyze the future outcomes of a component based on the present performance. That is how we try to develop the advanced analytic systems. And also we have been using the proximity sensors and cameras in certain applications. So there are like variety of sensors we use in the automotive applications. They help us in a big way, and the role of the engine speed sensor, how it helps us to monitor the rotating speed of the crankshaft so that the fuel injection and the engine timing could be controlled. And also we do have like spark knob sensors, which is used to ensure where the fuel burning is happening smoothly, otherwise it may lead to unexpected ignition and so on. So there are like different performance measures related to this Industry 4.0 based system in terms of dealing with the volatile conditions of the market, the technology adoption, and also the self-monitoring capabilities and the network flexibility and so on. So before we proceed with the discussion on the pillars of smart manufacturing, having discussed about the focus of smart manufacturing, some of the technologies, and also about the protocols and the applications, are there any queries from the attendees at this stage before we proceed further?
No, sir.
Okay. Right. Let me proceed further. So now let us spend some time on discussing the various pillars of smart manufacturing, starting from materials perspective, the data parameters, predictive engineering, manufacturing technology and process, and also like resource sharing and networking aspect, sustainability, and so on. So sustainability is a very important pillar of the smart manufacturing system, wherein we'll be spending towards the later part of the presentation towards like sustainable systems. So we could understand that there's a connect between the smarter systems and the sustainable systems. So when you look about the definition for smart manufacturing, as per the National Institute of Standards and Technology, US, it implies it's a completely integrated collaborative manufacturing system that can respond in real time to meet the changing demands and conditions in the factory, the supply network, and in the customer needs, which provides a comprehensive definition for smart manufacturing. And it shows some of the key terminologies associated with the smart manufacturing. So the principles, as we have discussed earlier, the principles are being presented for a smart manufacturing system. And we could see the rate of adoption of the emerging technologies in the present day use, and also the projection for a next couple of period is being given. We could understand like the role of the cloud systems, the inventory optimization systems, sensors, predictive analytics, Internet of Things like 3D printing and additive manufacturing, robotics and automation, they have some of a significant role in terms of developing like smart manufacturing system. So as we discussed, some of the technologies are being presented, and also here the role of this hybrid systems, wherein with a 3D printing additive fabrication system coupled with the CNC based system can facilitate the hybrid manufacturing in terms of going ahead with like precision parts. And also that is obvious in the context of like metallic components manufacturing, wherein the parts have to be produced very faster with a lesser material wastage. Of course, they need to be supported with the simulation-based modules and so on. And another interesting aspect is that from cyber physical systems, we have moved towards like cyber physical production systems, CPPS, in the context of smart systems, wherein it includes like autonomous and cooperative elements and subsystems that are connected based on the context within and across different levels of production. Thereby, they can help in the coordination of the process, starting from the machines onto a level of production and logistics networks. It takes across the spectrum of the activities in manufacturing. Of course, we discussed about like the role of AI and digital twins, and we could see an architecture of the data analytics-based cluster in the context of smart manufacturing, where we could obviously see the role of smarter materials, predictive analytics, the tracking and tracing applications, the knowledge-based systems, and so on. Okay. For the sake of time, let me just proceed with some of the clusters, and we can proceed with the architecture of a smart factory for discussion. Okay. This is how the architecture of a smart factory look like, wherein we do have like different layers in the smart factory. Starting from the terminal level layers, we do have like cloud application layers, network layers, and physical resource layers. We could see completely this digital twin of the products and process, and also the interfaces, the role of the communication networking protocols, the role of the Internet of Things and Industrial Internet of Things, and also about like Internet of Services. They help us in a big way in the execution of a smart factory. Let us assume the scenario wherein as a shop manager, we may have to take ahead with like several units which are located in several locations. Every location has a couple of layouts with different missions. As a shop manager, we need to monitor the kind of the conditions with related to the productivity, with regard to the quality, maintainability, and reliability, those measures, and how that is possible. Definitely, we need to take the help of the Internet of Things, IoT-based systems for the sensing and actuation modules, and how they could help, how they have to be interfaced with a cloud server, because ultimately they need to provide data update to the cloud server, and they will provide the information through the smartphone-based applications, so that the shop manager can manage different units or different which are in different locations, like operating like the context of virtual enterprises. That will help us understanding the technologies, how they help us, and not like a single technology, like multiple technologies. They help us in taking ahead with the vision of a smart factory. Okay. So here there are like several benefits of smart manufacturing in terms of like financial benefits, in terms of like resource-based benefits, in terms of like optimal energy consumption, efficiency improvement, and in terms of like lead time reduction and the cost savings and the return on investment increase and so on. And the application domains are diversified. Almost we could say like it's in like all industries and all industrial establishments they take ahead, including like a small and medium enterprises, small scale industries. We could see the implementation of this smart manufacturing. Even the small scale industries, they have interest. Only thing is that The challenge is that developing the technological infrastructure for them is requires investment. That is more challenging for them. That we should have a realization how we need to take ahead with the development of the smart factory, the developing the infrastructure. So like cluster of small scale industries, they come together, they try to develop the technological infrastructure where they go for like sharing of technologies, and such cluster based implementation also could accelerate the implementation of smart manufacturing across the industrial establishments, and it helps us in a very big way. Okay, so before I proceed with like the sustainable manufacturing module, the second module of my discussion, okay, let me spend some time in terms of responding to the queries. Okay, so let me just request some queries from participants related to smart manufacturing. As we completed the discussion of smart manufacturing, are there any queries from attendees related to smart manufacturing? You may feel free to ask questions.
No question, sir, till now.
Okay, so let us just wait. Let us see, like from attendees, are there any questions? You may unmute and feel free to ask questions. You may post in the chat box as well. Okay, like we could see, we could understand that there is a connection between the smart manufacturing and sustainable manufacturing. As we have understood, sustainability is also one of the key dimensions of a smart manufacturing system. That connect we could realize while discussing about the concept of smart manufacturing. So now let us spend time on discussing the scope, the concepts and the methods, the tools of sustainable manufacturing, and how it enables the augmentation of the systems in line with the goals of developing advanced factories in line with industrial developments. Okay, so let me just proceed, and maybe like any questions you may feel free to post in the chat box also, and let me internally take ahead. Okay, so the term sustainability has to be understood, which implies, normally we refer the Brundtland Commission's definition of sustainability, which states that we try to meet the needs of the present without compromising the ability of future generations to meet their own needs. So it has like three important dimensions. One is environment, economic, and societal sustainability. And we do have they three have a very strong connectivity. The environment dimension take care of the planet, the cleaner resources, with ensuring the ecological balance of the system. And the economy is about like the financial benefits in terms of like newer employment opportunities, like product and process innovation. The societal aspect is about health improvement and safety improvement and quality of life enhancement and so on. So this is called the triple bottom line approach, TBL approach of sustainability. And they have a strong connectivity among these three dimensions. So it is very obvious. Let us take a very common example to understand this triple bottom line approach of sustainability. Say, for example, we could see the industries, mostly like automotive, aerospace component industries. They work on with weight reduction projects, weight reduction initiatives. They work on a large scale in order to constantly reduce the weight of the products. Okay. Let me ask a logical question here to the attendees. Why such industries work on with this weight reduction projects? Why they want to reduce the weight, the context of automotive and aerospace systems? Yes. Will you please answer to my question? Why they work on with this initiative? Attendees, at least one, I can hear a response.
To improve efficiency, sir.
Good. Okay. Then, any other objectives? Okay. So here, that weight reduction is very essential in terms of like efficiency improvement, in terms of improving the performance of the product. And if we try to take this objective, then definitely in terms of environment, we try to reduce the resource consumption and we try to reduce the environmental impacts. And from economical perspective, it tries to reduce the cost and it provides the profitability and the financial benefits. And from societal aspect, we need to do this through the application of the robust optimization methods and techniques. And hence, that learning aptitude among the workforce is also very essential. Now we could understand that there is a strong connectivity between these three dimensions like environment, economy, and society to take ahead with the developments in the context of sustainability. Likewise, you can take any application, you'll be able to see a strong connect of these three dimensions. So now in the context of sustainable development, we do have like a triple bottom approach we understood. And technology is the base. And we do have like innovation and creativity is very, very essential, for which we constantly go ahead with education and training. There are like different applications in the context of sustainability. We, in the context of manufacturing, we call by the term sustainable manufacturing. We do have like sustainable energy systems, sustainable architecture systems, sustainable construction, and sustainable energy applications, and so on, like diversified applications. And the applications are increasing day by day. That's another interesting aspect of this sustainability in the context of the varied applications. And here, there are two terms we normally come across. One is like sustainable manufacturing, another one is like green manufacturing. There is some difference between these two terms. The green manufacturing is environmentally benign, which is 3R based, like reduce, reuse, and recycle. On the other hand, sustainability is coordinators, could you please listen to the interruption which is happening?
Hey.
The sustainable manufacturing is about like an innovative and creative system where the focus is on like 6R based. Then do we have like additional 3Rs like recovery, reverse design, and reverse manufacturing? So this difference is helping us to develop the sustainable manufacturing system with the various innovation elements, and the stakeholder value also enhances across the time frame. And the difference between the 3Rs and 6Rs, where the primary 3Rs are reduce, reuse, and recycle, and the additional 3Rs are recovery, reverse design, and reverse manufacturing. That is very important. And now we'll be discussing on a significant tool of sustainable manufacturing, which is called life cycle assessment, which is also referred as life cycle analysis, where the ultimate purpose is to find the environmental impacts associated with the products and process. So this life cycle assessment is very helpful. It's a very important tool of sustainability, wherein we have like 4 phases starting from goal and scope definition, inventory analysis, impact assessment, and interpretation. These 4 phases have to be done based on the ISO 14040 and 14044 standard, wherein the goal states that why we do an LCA study. Is it for the government regulation or for the overseas customer? That goal has to be specified. And also like this boundary definition should be made very clear. Am I doing within the factory, or I'm starting from materials and extending to manufacturing, or am I going to extend to use and end of life? That is very, very essential. The second phase is about like inventory analysis, where the term inventory is having a different context here, which accounts for the material utilization, which accounts for like a resource utilization, which accounts for like energy utilization within the process. That inflows to the outflows have to be very clearly understood. This inventory data is very essential. And the third one is about like impact assessment, where the relation between the inputs and outputs and the impacts have to be understood. The process models have to be analyzed, and accordingly we need to find the environmental impacts based on the impact assessment methods, which may vary from one geographical location to the next. Whereas in the context of US, they use Europe, they use CML method. In the context of India, we use like eco indicator method. So here, Once we are very clear with the impact assessment method and the impact categories which are interested, we can find the environmental impacts, and then we go ahead with finding the impacts. Any LCA study can help us to find about more than like 16 impacts we can find from an LCA study. But in the context of product design and manufacturing, we are concerned with the 4 impact parameters like carbon-based impact, sulfur, nitrous impact, and energy-based impacts. And the last piece is about deriving inferences, interpretations, and how to reduce the environmental impacts. That's more essential. Okay. This is a simple process model of a system, which is called the input-output model. IO model we call two-dimensional process model, where on the input side we could see the materials, energy, and the other resources. On the output side, we deal with the product and other related emissions and so on. But this two-dimensional process models are no longer sufficient. Even in the context of sustainability, we need to go for a three-dimensional process model, where we need to correlate the inputs, outputs, and impacts. This relation between the inputs, the outputs, and impacts is contributing towards the measurement of the impacts, and we can find the ways and avenues to reduce the environmental impacts. So such three-dimensional process models are very essential. And also now we are going ahead with the higher order process models, even in terms of like technology integration, how it contributes towards the process improvement and so on. So like this is something about a typical LCA study we have done. So normally this life cycle assessment comes as like modules. We call it as like software modules for performing the LCA. The screenshots which are being taken from a CIMAPRO LCA module, which is widely used in the context of a software module for performing life cycle assessment. So to a software module would be integrated with a database, so that once I specify the inventory data for my process, then the inventory data will be correlated with the impacts, and accordingly the environmental impacts will be calculated. So on the left is a automotive component being done for a case study, and on the top right we could see the various impacts pertaining to different process. The bottom left which shows the process model, and the bottom right which shows the unified impacts across these parameters like health, ecosystem, and resource-based impacts. This is more interesting to take ahead with the study. And finally, we can explore the ways and means to reduce the environmental impacts. So now, in the context of like a sustainability in manufacturing, as we have discussed about like a LCA study in the context of process, we do have like product-based life cycle assessment. We do have modules for finding the environmental impacts during the early phases of product development. Before we develop the products, before we do the manufacture of the products, how we can find the environmental impacts. We can do it. We can find. So such modules are available, wherein we need to provide the geometric model or data of the component, and then we need to specify the materials manufacturing process and the manufacturer user location, and accordingly the module will calculate the impacts across the life cycle phases like materials manufacturing, use, and end of life, and we'll be able to interpret which environmental impacts are significant during which phase and how we can reduce the environmental impacts and so on. So that is more interesting, where if we find the environmental impacts during early phases, that will help us to reduce the environmental impacts, the avenues, and thereby developing sustainable products and process is facilitated. So we do have from a life cycle assessment perspective, like product-based modules and process-based modules for performing the life cycle assessment. Okay. So having discussed about certain insights of sustainable manufacturing and about the life cycle assessment, and this in life cycle assessment we have discussed about like process-based life cycle assessment and product-based life cycle assessment, where the ultimate goal of LCA we have understood the environmental impacts, quantification and further minimization of environmental impacts, and the ways to reduce the environmental impacts. So now it has certain connect with like additive manufacturing. As we have understood, additive manufacturing has taken a pathway from prototyping, tooling, manufacturing, and so on. So now in the context of additive manufacturing, which is having the sustainability aspects incorporated, because the kind of emissions or the environmental impacts with additive fabrication is relatively lesser. Say for example, in the context of the process which use like support structures, where we can go for like optimal support structures, and also the powder bed fusion process where we have mechanisms for reusing and recycling the powders, and also we do have like mechanisms incorporated for optimal support structures and also like optimal material utilization in the context of additive manufacturing. Also, another important, interesting aspect in additive manufacturing is that during design phase itself, we can do this optimization. Because it provides additional perspective for manufacturing. And before fabrication, we'll be able to know the cost, time, and all other related parameters, and it will help us in developing the sustainable products. And as I mentioned, from 3-dimensional additive manufacturing, we are moving towards like 4-dimensional additive manufacturing, where the perspective is like utilizing the smart materials, smarter products, smarter process, and so on. And the next, another important aspect of in additive manufacturing is that designing for additive manufacturing, which is called like a DFAM. And as we have in design for manufacture and assembly in the context of the traditional manufacturing, like casting, welding, forging, machining, and so on. So in additive manufacturing also, we do have certain design guidelines, design methods, and design procedures, which can help us in improving the feasibility for additive manufacturing from a design perspective. And that could help us in developing the additive manufacturing systems or the products which can be facilitated from viewpoint of additive manufacturing. Thereby the feedback between the design and manufacturing activities could be minimized, and we could facilitate the development of designs which can be manufacturable using the additive manufacturing methods. So it provides like additional perspective. And let me just show one or two case studies in the context of this additive way of fabrication. Wherein for a rotary switch product, we did a case study. And this is on the left side, you can see the exploded view of the switch, wherein like the complete interconnectivity of the various components and assembly is being shown. On the right side, we have taken ahead with the customization of different components of the switch of the product. We went ahead with developing customized designs, and further we have gone to developing the customization module for the for the industry, and thereby the variants of products being manufactured or being presented. As a customer, they can select any product of their choice, and accordingly they'll be able to have they navigate through the complete exploded view of the product. So component by component, they can specify their choice, and they can specify their preference. So ultimately the code will be generated as per the customer's requirement, so that any kind of a change they want from a design perspective, from a geometric data, everything is possible, and accordingly such changes could be taken ahead, and accordingly the customization code will be developed for different customers. The customization codes will be gathered, and the commonalities will be analyzed, and then based on the algorithms developed, the designs will be fabricated and as per this customer's requirements. And this is something like the screenshot which shows the customized designs of the products being developed in line with the customer's preferences, the various designs. This is something like an example for how we go ahead with like a customization module in the context of manufacturing. This study helped the organization to develop a customization module to facilitate the designing and development of the products from customers' preferences. This is something like a solid dimension based printer where we designed and fabricated the components. It is something like the raw material is a kind of a PVC sheet. So the working mechanism of the device is that the layer of PVC sheet will be laid, and a layer of glue will be applied. And there will be a trimming knife which will cut according to the profile of the part. And there will be anti-glue pens which will remove the glue from unwanted layers. So that the next layer of sheet will be laid. So that as per the profile of the part, the sheets will be glued and the unglued parts could be removed at the end, peeled off at the end, and accordingly we can get the components. Of course, the orientation of components is also very essential. As I mentioned, this estimation of the parameters in advanced fabrication is possible in terms of like the time, cost, and other related aspects. On the bottom, you could see the prototypes of the products being developed, and there are like two goals of this designs being developed. The customers have visualized the designs, and the second is that the designs are being put for basic experimentation, wherein the torque application helped to fabricate the designs in line with the customer's perspective, and so on. And the second study we did for a pump manufacturing organization, wherein the focus was to improve the efficiency of the pump, where the casing and impeller designs are being shown. And we have gone ahead with varying the head and discharge parameters, and accordingly the different dimensions we could capture. And here we had like two important challenges in this study. One is about once I specify the head and discharge value, automatically the design dimensions, the design parameters need to be developed, for which we developed a kind of a computational support, which helps us in analyzing the characteristic curves of the pump, and accordingly, once I specify the head and discharge value, the dimensions of the impeller and casing are being developed, and accordingly, these are being given as input to the geometric modeler, and accordingly, the different designs are being done. The second challenge is that pertaining to the different dimensions of the impeller and casing, the designs need to be made so that we went ahead with utilizing the parametric design approach in CAD, and accordingly we could design and develop the varied designs. As we utilize the parametric design approach, it helped us in minimizing the development of multiple designs, as already the baseline design is being set. With the variations in the dimensions of the impeller and the casing, different designs are being developed and they are being subjected to the analysis. And the best design had been taken ahead with the deployment, and we went ahead with an extrusion type process like for fabrication. It is something that an STL file which is being shown on the top. On the bottom, we could see the kind of a fabricated impeller. So this gives us something like, with the fabricated impeller, we went ahead with secondary processing in order to improve the engineering properties in line with the requirements, and also that is being subjected to the testing, experimental testing in the organization, and accordingly we could facilitate the objectives of this design. This is something like the additive manufacturing facility we have in our lab and in our department. It's an FDM based machine, and the build size and layer thickness and other parameters are being shown, and these are some of the software interface wherein we could understand that the generation of the support structures is also very essential, and we have to generate the support structures in line with the requirements. And these are some of the components being fabricated in our lab from automotive perspective, unlike in medical applications. And we worked on with an automotive mirror development project and so on. Fine. So having discussed the sustainable manufacturing, we could understand the connect between the additive manufacturing. Why I've taken additive manufacturing for discussion is that it is being incorporated with certain sustainability characteristics. That's why I've taken for discussion. Okay, so are there any questions at this stage?
Sir, we have few questions in the chat box.
Please read the questions, sir, because I don't see my chat box.
Question from Kishore. What is the cutting edge technology versus near net computing?
Okay, so here, this in terms of the developing the computing technologies, we go at different levels. Even like presently we are going ahead with like supercomputing technologies, and also we do have the cloud-based computing mechanisms. Next we are proceeding towards the related technologies. I think these technologies can provide better and very good computational capabilities for developing the smart factory. Fine, sir. The next question.
From Raju, sir, how far a developing nation like India will...
Industrial revolution, it is something a continuation of the existing industry 4.0, but the dimensions or the focus areas are going to be like sustainability, resilience, and this human intellectual capability. So with this, as a sequel to the industry 4.0, we are going to take the industry 5.0, and already the the initiatives have started, and definitely we'll be able to go ahead with the deployment of Industry 5.0 in a short while. Yes, the next question.
Sir, question from Surinder.
Yeah.
What challenges industries faces to move from 3.0 to 4.0?
Yes.
Why not we go for 6D printing advanced technology?
Sir, the second part of the question, could you please read again?
Why not we go for 6D printing, 6-dimensional
Okay,
printing?
fine, okay, right. So this challenges industries they face in terms of moving ahead with Industry 3.0 to Industry 4.0 is that one of the important challenges is that developing a technological infrastructure. The second is that in terms of developing digital twins of the process, wherein the physical and the virtual scenarios have to be connected, have to be coordinated, for which you see with the CPS as a base. So here, the technologies are available, but in terms of deploying the technologies, depending on the situation and depending on the problem domain, that deployment relies on the creative and innovative thought of the workforce. These are all the challenges have to be taken. And the second part of the question is about like 6D printing. So now we have gone to a higher levels of utilizing 3D printing from polymers perspective, and we are moving ahead with metals perspective, and now we are taking ahead with the research on 4-dimensional additive manufacturing with the smart materials and other related shape memory polymers and the related materials. So definitely the pathway for other higher orders of additive manufacturing also will take place eventually. Yes, sir. Are there any other questions?
Next question from Uday Kumar. Sir, any developments from beginning of this subject rapid prototyping to now additive manufacturing?
Sir, will you please repeat the question?
Any developments from beginning of this subject rapid prototyping to now additive manufacturing?
Fine. Yes, again, an interesting question. As I mentioned, initially the technologies have been brought only for prototyping purpose. That is exploiting the prototyping activity of product development. Now, lot of developments have happened with regard to materials, with regard to the technologies, with regard to the architecture of the systems, in terms of elevating the capabilities of the system from developing a prototype to manufacturing of end-use parts in line with the industrial field conditions. So a lot of developments have happened, and the technologies have been developed, and the systems have augmented this transition. It's very obvious. It's again an interesting question. Yeah. Yes,
Is there any FEA possible for 3D printing technology?
Yeah, definitely. Because now, if you see, optimization is a very important aspect while performing, while designing for additive manufacturing. That's why we have brought a separate dimension. The separate domain is being brought under the design to facilitate additive manufacturing by the term DFAM. In DFAM, we do have different methods like topology optimization, generative design. These methods, they rely on the finite element modeling based approaches, and they are other advanced extensions of the finite element based modeling and analysis that helps us in designing and developing the products. Yes.
A question from Subramaniam. What are the drawbacks of 3D printing in sustainable manufacturing?
Okay. So this drawbacks in the sense, so with regard to like the methods which utilize support structures, now mechanisms have been brought to optimally utilize the support structures. Even in the context of powder bed fusion, earlier we don't have mechanisms for reprocessing and reusing the powders, but now mechanisms have been brought to reprocess and recycle the powders. So here, this additive manufacturing, it is being incorporated with sustainability aspect, and naturally this developing the advanced systems also fulfill this requirements of sustainability in a big way. And also the scenario is moving towards like need-based manufacturing, and definitely so additive and other related technologies also will comply with the requirements of the sustainable way of designing and developing products. Yes, sir.
That's it, sir. Please continue.
Yeah, fine. Okay. So now let me just play a video file with related to this the smart manufacturing, so that we can have the perspective of the smart manufacturing. Just a moment. Let me just play the video file. I'm opening the file. I hope the video file is visible.
Yes, sir, visible.
Okay. Let the video get played.
What video is this?
Yes.
Sir, voice was not coming.
Voice not coming, sir.
One second. Yes, yes.
Audio not receiving, sir.
Oh, let me just check it. I think the settings are fine. Okay. Okay, not an issue. I can just explain. I can play a first part and then I can explain. Not an issue. Okay. Fine. Okay, this first part of the presentation of the video file contains the developments that is based on the scenario prior to Industry 4.0, the complete sequence of activities involved in manufacturing the cars, every stage, what happens, and what are some of the basic technologies being adopted, and what is the real motivation to take ahead with the Industry 4.0. Now let us listen to the second part of the presentation. I can give a briefing at the end.
Sanju sir.
Fine. In the second part of the presentation, we could see the Industry 4.0 based implementation in the organization. We could see many of the technologies which we have discussed, starting from the robots, collaborative robots, additive manufacturing, powder bed fusion process, sensors, RFID based systems, simulation modules, IoT based systems, simulation modules, cloud computing based systems. And also they have mentioned that this Industry 4.0 and smart manufacturing creates a lot of newer opportunities and lot of newer developments. Okay. So, in a nutshell, we could understand we started with the discussion on smart manufacturing, the concepts, the origin, the technologies, and we went ahead with the discussion on sustainable manufacturing, the perspective of sustainable manufacturing, the life cycle assessment, and also we've taken the example of additive manufacturing, how it helps in sustainability and other perspectives. So, this integration of the smart and sustainable system, we are able to realize. That's the reason I have taken additive manufacturing as an example to show the kind of interconnect between the smart systems and sustainable way of designing and developing the products. Fine. So I think we are on time. So if I have any queries further, I'll be happy to answer to the queries. So participants, any queries from your side?
Thank you, sir. Now the forum is open. So the participants can raise your doubts and questions.
Sir, one more question in the chat box.
Yes, sir.
Is AMT, additive manufacturing, there is a change of process parameter possible?
Yeah, in additive manufacturing, yes, because we could see that in the systems, say in the extrusion type process also, earlier we had a single level of layer thickness. Now we can go to 3-4 levels of layer thickness we can set, and also the material combination also we can try. Likewise, the process parameters also we go ahead with the scope for enabling the optimize the parameter setting and so on. Yes, this is possible.
Question from Surya Subramaniam. Is it possible for composites through 3D printing?
Yes, yeah. This composite parts manufacturing is also possible through 3D printing. The composite filaments are also being developed and they are being subjected for fabrication using the technologies. Additive manufacturing is also being used for composite parts fabrication.
A question from Naga Sarath. Do polymers have an option in this manufacturing process, sir?
One second, sir. Will you please repeat the question?
Do polymers have an option in this manufacturing process? Smart manufacturing.
Yeah, that's the reason I have taken additive manufacturing as an illustrative example to show how this product performance improvement is possible in the context of smart manufacturing. And definitely from an additive perspective, even polymer parts fabrication, this we go ahead with developing smarter systems through technology integration, depending on the application.
Thank you, sir.
Yes, sir.
Now I invite Dr. D. Bhanuprakash, Professor, to give vote of thanks.
Thank you, sir. On behalf of management, principal, vice principal, and department of mechanical engineering, Swarnandhra College of Engineering Technology, Narsapur, Andhra Pradesh, we extend our heartfelt gratitude and sincere thanks to our today's speaker, Dr. S. Vinod, Professor, Department of Production Engineering, NIT, Tiruchirappalli, Tamil Nadu, who has shared his expertise in this knowledge-sharing platform on smart and sustainable manufacturing. Sir, your session was incredibly informative and thought-provoking. We are grateful to you, sir, for accepting our invitation at short notice. Thankful for your representation, being a session speaker in this FDP. Thank you, sir, once again on behalf of our organizing committee and on my behalf. I extend my sincere thanks to you, sir. Thank you, sir.
Fine, sir. Thank you. Before I hand over the session, I would like to convey a message to the participants. In this kind of FDPs, whatever insights we take ahead, we may offer similar courses, or we may plan to offer new courses in teaching. Definitely, we should explore. And also, like the research avenues who do research in this area or who would like to take up research, it provides a lot of avenues. And also, like projects jointly with industries, it's possible. So this kind of FDPs, they help us in taking these initiatives from all these perspectives. Definitely, I request all of you to utilize these sessions and take ahead in your career. Thank you so much. I would like to thank the coordinators, in specific Dr. Sanjeev Kumar, for inviting me to deliver this lecture. Thank you all. Have a fine evening. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Yes, sir. Sir, I'm leaving the meeting. Thank you.
Okay, sir. Okay, thank you.
Thank you, sir.
Now the feedback and attendance link will be posted in the chat box. So it will be active for the next 15 minutes. Now the feedback and
Good evening, sir. Welcome, sir.
Yeah, good evening, sir. Good evening. I'm audible to you?
Audible, sir.
Okay, thank you.
now it's my pleasure to invite Dr. R. Lalit Narayana to introduce our Day 4 Session 2 resource person. Sir, please.
Okay, sir. Good evening, all of you. I am Dr. Lalit Narayana, Professor in Mechanical Engineering Department, Swarnandhra, Nasapuram. I am deeply honored to introduce our today Session 2 speaker, Dr. Ravi K. Petala, Associate Professor, Department of Mechanical Engineering, NIT Warangal. He specializes in fluids and thermal sciences. He completed his Bachelor of Engineering in Mechanical Engineering from Andhra University in 2006, followed by MTech and PhD in Fluids and Thermal Sciences specialization from IIT Guwahati in 2014. Later, he worked as a scientist in ABB during 2014 to 2016. He worked as an assistant professor VNIT Nagpur during 2016 to 2018. He worked as assistant professor VNIT Nagpur as AGP 8000 during March 2018 to June 2022. He worked as associate professor AGP 9500 VNIT Nagpur during June 2022 to October 2022. Currently, he worked as working as associate professor, NIT Warangal from 2022 till date. According to research, he completed one DST project during 2017-2020. We have two ongoing projects. One is development of in-house three-dimensional non-equilibrium solver for hypersonic flow applications, and second one is fluid structure interaction studies of FASU flapping in flash population. According to academic awards and honors, he selected for fully funded research opportunity week at TUM Germany in 2014. He is recipient of SERB under ECR by DST New Delhi during 2017-2020. Development of in-house three-dimensional non-equilibrium solver for hypersonic flow applications, ARDB, Government of India, during the period of 2024-27. Next, one more. Fluid structure interaction studies of PASU flapping in fish population propulsion, THIIT Guwahati, during the period of 2024 to 2026. He supervised one PhD scholar and three ongoing PhD scholars. He supervised 8 MTech projects and ongoing two MTech projects. Ongoing researches: design and fabrication of thin film sensors for hypersonic flow applications. He published 20 essay journals and 13 conference papers. Ladies and gentlemen, let us welcome to Dr. Ravi Kumar for the talk. Thank you, sir.
Yeah, good evening. I'm audible to all?
Yes. Sir.
Okay, thank you. So thank you so much for giving me opportunity to give the expert lecture in this platform, and I especially thank you to Principal Sir Suresh Kumar and Gopal Sen Sir, Vice Principal, and Convener Francis Yodarki, and especially a special thank to Lalit Narayan Sir and Sanjeev Kumar Sir and co-coordinators. So thank you so much for giving the opportunity to share my thoughts in the field of thermal management of lithium-ion batteries. So, just are you able to see my screen?
Yes, sir.
Okay. So my topic is thermal management of lithium-ion batteries. So as I said, I'm associate professor at NIT Warangal. So this is my outline of presentation, introduction. So in this introduction, I'm going to explain about what is how the thermal management is required for the lithium-ion batteries or EV vehicles, and what are the issues are facing so far in these situations, various countries, and maybe especially in India. What are the issues we are facing, thermal management issues in the electrical vehicles, and based on that, what we are doing here. So I want to frame some objectives of addressing that issues, and how we are approaching that. Problems using mathematical modeling. So basically, we are doing with numerical simulations. So mathematical models and formulations, so what we are going to use for to develop the or address that issues, we are using different mathematical techniques. And we do study the numerically, we study the battery thermal management systems. So what is the battery thermal management system, I'm going to explain to you. And after that, so there are one more thing is like suppose there are some accidents or something like charging and discharging condition, we are drawing more power from the stations or maybe more power from the engines. There are temperatures are drastically increases. Due to that, due to inside the chemical reactions, maybe some mechanically it is happening some accidents. So the battery started getting heated drastically due to exothermic reactions of the inside the battery. Then temperature drastically shoot up from room temperature like 80 degrees to 1000 degrees centigrade. There is called thermal runaway. We are going to explain. I'm going to explain that what is meant by thermal runaway, how to address, and what kind of cooling techniques we need to use for that situations and all. So finally, references where I use this, where I refer some references. So as you know, the growing the pollution is drastically increasing, and climate changes are observed. As you know, the temperatures are shoot up like 40 degrees, 45 degrees, and so. So many countries have started adopting the mitigation strategies to achieve the zero pollution by 2050. So encouraging the use of EVs is one of the effective mitigation strategies for combating the air pollution. So as per the records or the studies from 2019 to 2024, the global electrical vehicles sales grew up around 506%, and the electrical vehicles mainly use lithium-ion batteries are used in the electrical vehicles. There are superior features in the lithium-ion batteries. Here, there are high energy density and higher stability, a longer life cycle. Charging and discharging cycles are we call it cycle. There is a longer cycle, low self-discharge rates. These are the advantage of use the lithium-ion battery. So a lot of research work is going on in the globe in the lithium-ion batteries and thermal management systems. So here I showed some figure here, the battery performance versus the temperature at the x-axis. So operating temperature, desired operating temperature of my lithium-ion battery, 15 degrees centigrade to 35 degrees centigrade. If it is reaching above that or maybe 40 degrees, they started. There are thermal management is required to maintain that this within the range of 15 degrees to 35 degrees. Maybe it is 40 also, it is fine. So if you should not go more further, such that the battery started decaying, and maybe some hot spots may observe this, due to that the thermal runaway will start aggregate. So due to that reason, we have to maintain the proper heat transfer within the lithium-ion battery. So we are not using only single battery to run the electrical vehicles. We use multiple cells. So and multiple cells, how we arrange and how much power we draw from that back. There is a temperature rises will take place by 5C rate, 2C rate, 1C rate. Based on the drawing power, charging and discharging with various rates like 5C rate, 6C rates and all. Then it is the temperature rises are observed. So we want to make the proper thermal protection system of the electrical vehicles using lithium-ion batteries while using it. So how the working principle is the charging and discharging, how it is happening. There is a anode and cathode and separator, and there are electrolytes. The electrolyte process from charging condition, positive electrode to negative electrodes. When it is discharging happening, and negative electrode, the electrodes are processed from negative electrode to positive electrode. This is the working of a basic working principle of the lithium-ion battery. So there are different types of batteries we can see here. There is a prismatic cell, which is this prismatic cell, and this is a cylindrical cell, and pouch cell, and bottom cell. These are the cells generally used in the automobile industry. Mostly they use uh, cylindrical and prismatic cells in our automobile industries. So I want to focus on these two. So where the failures are occurring, just I have shown some figures. The source is the some document, internet I gone to that. So these are the failures occur in the various conditions. Like suppose while charging, the thermal runaway means that the burning means thermal runaway, that heat transfer. Maybe this we can say that thermal runaway is happening while charging, and here while driving there is a short circuit. Due to that, the vehicle is started burning. When it crashing, this crash, due to that thermal runaway temperatures are drastically increases inside the cell, so there is a there is a failure, thermal management failure, so we can see. And here your image is the burning of the electric two-wheeler vehicles due to the failure of the thermal management. So these are the examples I shown here. So it is happening in everywhere in the world. So especially in India, there are so many cases observed for the failure of thermal protection system of the vehicles, electrical vehicles. So there are various ways to use thermal protection system, which are that I'm maintained here. There are I'm showing here the figure 1 shows that BTMS, which means battery thermal management system, used in the 3 different kind of cooling techniques, which are passive BTMS and active battery thermal management, hybrid thermal management. So passive cooling techniques, we use the PCM as a material over the surface of the battery to extract the heat or dissipate the heat to the PCM from the cell. We use the PCM and heat pipes that we are using. These are the active passive cooling devices, and active cooling devices, we supply the air over the surface of the cell such that we can remove the heat from the cell, and liquid cooling. So sending the cooling of the battery pack, we need to use some kind of device or some kind of power we have to give to the fluid such that it passes over there. That is the reason we use the active cooling or active PTMS. Hybrid means the mixing of these two. We call it as hybrid. So we are using air and PCM, liquid and PCM, heat pipes and PCM. These are the combination of these two. We call it as a hybrid. So these are the advantage and disadvantage of the various cooling techniques I reported here. And advantage, air cooling is lightweight and but with low thermal conductivity. So cooling is not it take long time to cool it. And compactness, if it is the compactness, because if you want to use in the two-wheeler liquid cooling, we need to use some pumps to supply the fluid or the battery pack. We need to add one more device to supply that. So it is sometimes it leakages and corrosion resistance in two-wheeler. But in case of four-wheeler, liquid cooling is also good, and PCM also good in both the ways. And but is low thermal conductivity of the material for the PCM, where especially in the food cooling, cooling and leakage may take place. So heat pipes we use in electrical electronics and these electrical applications also. But it is a complex, limited cooling expense. It is expensive also, limited cooling as well as expensive. These are the advantages and disadvantages of battery thermal management system of the different cooling systems. So as I shown here, there are passive coolings here and active coolings here, and there are hybrid coolings. How the arrangements is happening, made it in the actual cooling systems. The passive cooling, there in between the PCM they added, and here also the cooling devices. So here they use in between they use various cooling systems. So as I said, thermal runaway is self-sustained. What is meant by thermal runaway? So here I shown here. So the thermal runaway self-sustained and heat amplifies the reaction within the battery because of the chemical reactions. It occurs excess heat generated within the lithium-ion battery. The amount of heat dissipated in surroundings, it can be lead swelling and leakage and fire, even explosion it takes place. So these are the issues happening very high. And again, thermal abuse due to the overheating of the battery. So these leads to the thermal runaway. These are the causes, mainly thermal abuse and electrical abuse and mechanical abuse. So if it is happening, then thermal runaway is occurring, and due to that, the temperatures are drastically increases. As shown in figure, standard operation is as follows, and heat dissipation rate is higher than the heat generation within the cell. Then our battery pack is safe. If it is not, then these are the issues are observed. So this is the introduction part of that's how the PCM will work. So PCM is works like solid. The PCM is started. We phase of the PCM is solid, and observe the heat and is dissipating the heat and various regions like sensible heating, latent heat, and so on. So the cooling is happening here. The working is called PCM, and reverse is happening. The temperature drop is happening again. It is converted into liquid to solid. This is what happening in the, but reverse happening the liquid to PCM should be come back to the liquid to solid. This process take use time comparatively this. So that is the reason there is a drawback of the PCM. So these are the mechanisms. So there are different types of PCMs are used, which are organic PCMs, inorganic, and aquatic PCM. So the paraffin compounds, non-paraffin compounds with the organic PCM materials, and salts, hydrate salts, and molten salts we use an organic, and metals and alloys use an organic PCM. So these are the advantages of each material. Based on your application, we have to choose as a PCM material, how much it is we have to take out. So based on that issues, we frame some objectives, which is we develop the models. So we develop the battery pack model to study the thermal performance of the battery module, and we use different cooling techniques to make the working condition, or we can make the working temperatures. We use natural convection PCM with a different discharge rate like 5C rate and 6C rates. But how much energy we are drawing from the battery, or giving the charging to the battery, it is faster rate such that because we are sending more power to the system, such that temperatures also increase due to the resistive losses and other things. So we want to see what is the effect if we use the different charging rates, or if we make them more faster rate, how the temperatures are rising, and how to cool it. That is what we want to study, and the effectiveness of PCM and natural convection and cold plate strategies for the battery pack, and to analyze the thermal runaway battery pack with respect to change in heating positions, because where if it is the cell is there, where if it is heated, with heating is started, and how the heat is dissipating in the various regions in the pack, or in single cell also we did. So thermal runaway with modified designs, and we want to, because thermal runaway the temperature increases, and we want to minimize the thermal runaway, or we want to stop the thermal runaway, or we want to neglect the thermal runaway with the help of the cooling system. So we work with various cooling systems with modified design of the pack with air cooling systems. We're using the baffle plates to circulate the more air over the surface. We use the baffle plates. So how much heat is reduced, or how much heat is dissipating from the cell, we see, and we come to know that some conclusions we drawn with them. So these are the mathematical equations we use to study the thermal heat transfer distribution within the cell, and these are the mathematical equations for the PCM. These are the governing equations, continuity movement of energy equations. And I come back to the numerical studies of battery management system. So these are the battery. I use single cell battery. So first I took the single battery, and these are the material properties, and I validate whatever I am doing is correct or wrong. We have to cross check for thermal management system. So I use I started doing some validation cases. So we did the dimensions are as shown here. So these are the battery materials, and and the properties. So we did the grid independent study. Numerically, we done the simulations, and we grid independent study. We done that there is no change further after 40 lakh grid. So we choose 40,000 as a grid size, and we validated our results with Ogar Mulari in 2002. We published 2022. He published. So it is matching well. So how the temperature is rising from 294 to the 1C rate to 10C rate. So these are the temperature rise at 6C rate to 10C rate. This is the temperature rise from various conditions. Like this figure is drawn at the 600 seconds. That's which is temperatures rises is observed from the various discharge rates at 600 seconds. And now this is without PCM. Now I added PCM, and how much temperature we reduce. So that is what we did. So this is the thickness of my PCM is 3 mm I use, and these are the geometry. This is side view and this is front view, and these are the materials. There's a positive and negative tab and material, the battery material, and HN materials that we use PCM. So we validated with other literature. Ushen et al. He published, and how the temperature is increases when you use the PCM with various atmospheric conditions. The atmospheric temperature is reaching from 27 degrees centigrade to around 40 degrees centigrade. How the temperature distribution happening in the within the cell. So the temperatures are observed. The minimum is at 10 minutes. The temperature is 300 for the room temperature of 327 degrees centigrade to 40 degrees, as shown here. So this is the single cell battery validation I have done, and I can we further studies we had in the natural convection. Without PCM, we use natural convection. The surface heat transfer rate is I use 10 watt for heat transfer rate from battery to atmosphere. The heat transfer rate H is used 10 watt per meter square Kelvin, and ambient temperature I consider the 25 degrees centigrade. I use King model and GGKT model for the numerical simulation. These are the material properties I use, and we tested our various C rates, discharge rates with respect to time. It is well agreed with respect to time how the temperatures are varying from the various C rates. We can observe the maximum temperature is within the limit, which is 310 Kelvin, which is almost 35 or 40 degrees centigrade. So here I have shown here the maximum temperature in QC rate we observe in 38 degrees centigrade at the 1700 seconds, and in case of 3C and 4C, the maximum temperature observed 46 and 57. So these are the simulations we validated with the Panchal and Jiang et al. So now I use these are without PCM or without any, only natural convection I consider. Now I use 3C and 6C rates using various PCM materials. So here I added PCM such that the temperatures are drastically decreases from the battery temperature drastically decreases from 332, the maximum temperature 5C, 332, 350. Around 15 degrees drop is observed when I use the PCM material. Like suppose here 340 without PCM at the 700 seconds, the temperature is 327. But in case of various PCM materials I use, for 1 mm thickness and 5 mm thick up to 4 mm thickness, it is observed around 314 or 313 temperature rise at the 700. So we come to know that when you use the optimum PCM thickness over the cell material, over the surface of the battery, I can able to make the temperature within the limits of the operating temperatures. So that is what we observed here, and these are the how the liquid fraction means how the PCM is converted to liquid or liquid to liquid in the while going to the heat, how the heat is dissipating from the cell to PCM. So here I showed various PCM thickness, 1 mm thickness. So more 75% of solid PCM is converted into the liquid. In the case of 3 mm, 5 mm, it is 40% of PCM is converted into liquid. In case of 5 mm thickness of PCM, it is 29%. So this is the variation of the PCM material, PCM, and here I shown here the same graph I projected here, percentage of with respect to time, how much from 350 to 380 seconds they started melting, the PCM melting here. But in case of 3 and 5 mm thickness, the PCM is started melting at 600 seconds. Till that time, the PCM will in the solid phase. So far, you have any questions? So if you don't have any questions, I have just same strategy applied in the battery pack with the 2C and 6C rates, and how the temperatures are increases as I shown here. See, the temperatures are at 3000 seconds also. The temperatures are within the limits. If you draw the current or charging the current battery and recharging and charging 2C rates up to 200 seconds, there is no issue. But in case of 6C rates, the temperature of the battery is shoot up even 100 degrees, 1000 seconds itself, that shoot up around 330 degrees centigrade, close to. So it is not suggestible to draw the current that much, or we have to use proper thermal protection system to maintain the temperature within the limits. And how the discharge rates is happening from voltage 32 volts to various C rates, how much discharge that are in 6C rate, the discharge is within 10 minutes, the discharge is happening. Whatever the energies were stored in the battery, we discharge in the within 1000 seconds. And accordingly, the temperatures also rise up very high comparatively to C rate. So this is what all about the temperature distribution in the battery pack. Do you have any questions?
Sir, we have a question in the chat box from Uday Kumar. What is the latest trends and research future in this area?
So these are the latest trends. Maybe people have started using other material batteries also, but so far the automobile industry they use in the lithium-ion batteries mostly. And there are some more research is happening in the, but still not they're not used in any automobile. But there is under research. It is a solid state battery. Solid state batteries they use that, but that is also it is under research only, not public. So these are the lithium-ion batteries, the battery packs they use in our automobile industries like electrical vehicles. Any other questions?
Yes, a question from Justin Josh. Is it advantageous to use solid-to-solid PCM for the thermal management?
Yeah, solid-to-solid PCM means that question is related to means solid phase or liquid phase. That is what? No, if it is dissipating fastly if it is in solid phase. So after that you have to dissipate the heat from the PCM, right? Outside. That dissipation is, you have to remove the heat, then only it is come back to the solid state, right? That is that we observe the heat fast from this battery and it started melting. After the melting temperature maybe 80 degrees centigrade, let us paraffin is 80 degrees centigrade. Once it reaches the 80 degrees centigrade of the PCM, they start melting. That melting is happening if you increase the temperature and heat is then after that you have to remove the heat from the PCM also, right? Otherwise heat will be transferred backside, right? If it is cool. So that cooling is that removing the heat from the PCM and the liquid phase is difficult. And it is slow process. If it is in solid, there is no issue. Am I answering his question, or he have another question? Hello. Shall I move further?
Yeah, please continue, sir.
Okay. So these are the. Now I'm using the PCM over the surface. These are the PCM material, and in between the PCM we arrange in this fashion. The batteries are arranged with series and parallel conditions. So the temperature it is 330. Now within 3C rate, the temperature is like suppose this is let's say this is 3C, and in the 3C rate, the temperature without PCM it is this much, it is 370, and with PCM the cooling is using PCM that are 310 or 311. And so as shown here, it is in the temperature ranges in the various discharge conditions, which is as shown here with the PCM. The maximum temperature is observed in the 6C. The 3C is like this, but if it is 6C, as shown here, 6C, the temperatures are suitable. This is 3C is 320. So I compared with PCM, without PCM. Without PCM, the temperature rises around 314, 311. So this is they will use further time step, and the temperature if we use for 6C, the temperatures are very high. Here we can see temperatures are 330 Kelvin. So while using the PCM, the temperatures are within the battery pack, the temperature maximum reaching up to 316, not more than that. So we are able to control the temperature, or we are able to dissipate the heat within the operating condition. So we can say that the PCM is good for the cooling technologies, or we can say that this can be used for the battery packs for the thermal production systems. So this is the summary of the that simulations. So we investigated the cooling performance of natural convection PCM based cooling at various discharge rates. Discharge rates are 2C to 6C rates we use, and the key simulations simulation outputs are observed. The temperature distribution, thermal gradient, and PCM efficiency we observe. There is the natural convection cooling affected low discharge rates. If we increase the 4C and 6C rates, the temperatures are hotspots are observed within the cells. So the cooling, natural cooling may not be sufficient to address the thermal production, address the hotspots in the battery. So if we use the 6C rate, the temperature reaching 45 degrees Celsius, it is not good for the battery. The life will be decreased, and maybe thermal runaway may take place if I use if you draw the more power from the battery cell, and this is not suggestible for the 6C rate for natural convection. And in case of battery pack, if it is hotspots are observed in the middle of the cells due to airflow restrictions. So hotspots are observed in the battery packs in the middle of the battery pack. Is the battery pack around 16 by 16 or 16 by 2? So there are in between. The proper cooling is not there, means the temperature increases. So one of the battery in the middle of the battery, in the pack, the temperatures are drastically increases because of air restrictions. If at the 6C rate, the temperatures are increases above 50 degrees centigrade. Due to that, the failures are increasing the failure risks, and the thermal runaway may take place. So in this case, we conclude that the natural convection can be suitable for low discharge rates. If we want to discharge more current or more power from the battery pack, we supposed to use PCM material or other cooling techniques to maintain the proper thermal productions or maintain the temperature within the temperature in the operating limits. So then we use PCM in the various C rates like 5C rate and 6C rates. So 1 mm thickness, we consider minimal effect and rapid saturation is observed at a high discharge rates at the 5C and 6C rates, and minimal effect, and all the PCM is converted into vapor. Saturation is happening. So 2C also it improved, but at the insufficient for the in the PCM thickness for the 5 mm or 5C rates, and 3 and 4 mm thickness of thickness, the most effective in the keeping temperature below 45 degrees, but it will increase the weight of my battery pack. So weight of the battery also we need to reduce that for the automobile industry, right? So this is the drawback. If we use more PCM material over the battery pack, then weight of the battery pack will be increased. And so as I conclude here, 3 mm PCM up to effect up to 4 cm, but struggle at higher rates, and 5 cm optimum balance. The minimum temperature is within the 45 degrees. Over the time, the heat is observed decrease. Over the time, PCM is heat absorption is decreases, reducing the cooling efficiency. That is what I said. The PCM and cold plates may be. So over the time, the PCM, what is happening? The observing the heat is decreases and reducing the cooling efficiency. So for that, I can combine the two different cooling techniques, which is cold plates and PCM. If we add it, then we can use more appropriate way or more optimum way to develop the thermal protection system. So far that is the battery management system. Now, if the temperatures are increases due to the various reasons, like the various reasons, which is power charging, power discharging, maybe some accidents. In that case, the temperatures are shoot up, like from 30 degrees centigrade to 800 degrees centigrade. That is called thermal runaway. So we want to see how to mitigate the thermal runaway using various cooling techniques. That is what all about this portion. So lithium battery for higher energy, as I said, have lower thermal stability and safety risks while happening thermal runaway. Thermal runaway in the lithium-ion batteries involves there is a inside the battery exothermic reaction takes place because of the failures, mechanical failure, electrical failures, or thermal failures. Due to that, chemical reaction, exothermic reactions takes place. Due to that, inside the battery temperatures are shoot up. So the temperatures leads to the destabilization and degradation of the battery, as well as sometimes fire actions may take place. This is the schematic of various conditions. Like suppose this is the battery is having overheated or maybe defect. The temperature is drastically increased because we are charging faster rate, or maybe it is charging, but this cell is charging faster. Then after that, still we are giving the heat to deal power to that battery. What will happen? That power is converted to the heat. That heat is started heated, and due to that temperature, certain temperature, then inside the chemical reaction takes place. Then thermal runaway propagate, and the thermal runaway propagate nearby cell like this. So I started with simple. I want to understand how the thermal runaway mitigate. So intentionally, I heated this surface. We heated this surface, and I use lithium cobalt as a cathode material and nickel cobalt as cathode material, and I choose Hong et al. Paper. So these are the properties I use for my simulations, and I heated this surface with various heating rates like 1000 to 5000 watt per meter square. So how the temperature inside the battery I observe. So I done the grid independent study. The maximum temperature is reaching 1222 Kelvin. After the temperature started increases from 5000. This is the temperatures. Temperature is remain constant after 1 lakh grid points. If I increase the grid point further, also there is no temperature. Maximum temperature is not observed. So it means it is independent of the grid. So if you increase the grids also, the properties are not changing, means that is called grid independent study. So I done the grid independent study such that, so we come to know that at 10 lakhs, 23, yeah, 1 lakh grid points is sufficient for to do the simulation. So that is what numerically we understand that how many grid points is required to do the simulation in this battery. So I compared with Khang et al. So the temperatures are, see here, 400, the temperature is increases up to 100, maybe one, let us assume that is 100. After that, temperature started shooting up, and at around 350 or 370, the temperature is shoot up very high, which means thermal runaway started here. Up to the temperatures keep on increasing immediately. The thermal runaway means exothermic reactions are takes place, and temperatures are shoot up around 1000 degrees centigrade, or close to 900 degrees centigrade. So these are the thermal runaway happening in this point. So we want to, and this is another cell, NAC cathode material I use, and 1000 watt I use, watt per meter square I use, and what is the thermal runaway, where it is occurring, I come to know the points. So what I did, instead of being one side, I started, because the battery may hit at any place, right? Because of the proper defect battery may happening in either bottom of the battery, maybe temperature rise is happening in bottom of the battery, or from the bottom for 10 mm thickness, maybe by in this area or middle portion or this side. We don't know. Just I want to understand if bottom is started heating or getting heated, how the temperature is, how temperature increases. So I intentionally give the heat this bottom surface, and from the bottom 10 mm, sorry, for 10 mm from the bottom, I applied heat, supplied heat from 1000 watt for to 5000, and similarly middle, and which one is more dangerous or more effective, means where the more heat is absorbed in the various regions. So that is what we did. So here I choose Na cathode material as a cathode material. I use nickel cobalt material. As I observed here, I use heat. I give the heat from 2000 to 5000 watt per meter square. So the heat is given. I heated that surface 2000 watt per meter square to 5000 per meter square to mimic the thermal runaway. So as is seen here, 2000 watt per meter square, the temperatures are at the bottom, heating condition, the temperatures are not rising much up to, let us assume that 600, sorry 500. After that they shoot up. So I give more heat to the system, more heat to the battery, and the thermal runaway start much earlier than the 2000, which is with 5000 watt per meter square. The thermal runaway start below 200 seconds, maybe it's 180 seconds. The thermal runaway is observed in between these two. So similarly, I at the 5 mm width vertical heating is happening. So here the vertical heating condition. This is the vertical. This is the one case, and this is the another case I choose here. I plotted here. Sorry. Okay. This is the bottom heating. So this is the first case, which is bottom heating. The bottom from the bottom 10 mm width. What is the temperature? So from the bottom, and it is thermal runaway is more aggravated or more early it is happening. It's the bottom heating in this region. Bottom heating happening, bottom 10 mm, we are heating the surface with 2000 to 5000, and when 5000 watt per meter square, we are giving the heat to the bottom surface, and with below 100 seconds, the thermal runaway is happening and shoot up the temperatures of the battery, which means thermal runaway is occurring. So these are the conclusions. Thermal runaway here means thermal runaway triggering time bottom heating is faster than the 71.3% faster than the 2000 as you see. It is very much faster. So thermal runaway is triggered the time for bottom 10 mm of heating, 56% faster rate it is happening. So as the trigger time, the thermal runaway trigger time for 10 mm bottom heating advance, it is reach much 18 seconds earlier than the bottom heating. Uh, Earlier means bottom heating condition at the 500, which is faster than the previous. So now I use midpoint, the width at the center, how the if I give the heat to 10 mm, and this is the thermal runaway conditions. So it is 5000. The thermal runaway is happening before 200 seconds. In case of vertical at 5 mm thickness, vertically I heighted the surface of the my cell, and the thermal runaway is started at the 5000, which is 300 seconds. Before that, but before 3000 itself, when 2000 watts we given also, the center we heated, the thermal runaway is observed. So these are the conclusions we draw. Distant view. What is our intention is here is how when thermal runaway is happening, if various locations heating is happening due to the chemical reactions. So that is what we had. We saw that at the bottom 10 mm thickness and center as well as bottom, exactly bottom, the thermal runaway is happening is very fast without any cooling, without cooling. So these are the conclusions. So here we see bottom 10 mm thickness, the thermal runaway much earlier is happening, the middle second, and bottom, only bottom heating, it is further delay the thermal runaway or the temperature shoot up. If it is in the vertical 5 mm thickness, a thermal runaway happening around 350 something. So this is the we conclude that when you heating is happening in the battery surface at the bottom 10 mm thickness, then thermal runaway is happening much earlier than the other three cases. So these are the heat release rate inside the battery. What is the heat release rate in the various materials like separator, negative solvent and positive solvent electrode, and these are the temperature rise is happening in between 1000. Heat rise is happening from 150 to 180, and from the source also the temperature is happening in the same fashion during the thermal runaway. So this is the how the materials are inside the battery. There are different materials like electrodes, cathode material, anode material, complete thermal runaway. See here, the thermal runaway initiate here, and then electrode will start breakdown. The separator electrode will be breakdown, and cathode and anode material started decomposes inside the battery, and the combustion, that the firing is happening or the burning is happening. This is called complete thermal runaway. Thermal runaway over the temperature is increases over this. So these are the cylindrical modules because here I use coolant flow. So as I know, the temperatures drastically increases. So I want to use the cooling. So I want to reduce the thermal or delay the thermal runaway or eliminate the thermal runaway while using various cooling techniques. So I use here coolant water or air, sometimes where we use. So we supply the air in this channel, so that we are cooling is happening in the uniformly all the battery pack. So this is a mess, and I done the grid independent study. It is then I compare my results with open literature, which is Jing et al, and which is well agreement with their results, and temperature is increases from the various mass flow rates, which is hardly 35 degrees. So these are the temperatures we observed in the temperature contour, and the complete module is shows like, because here we are supplying coolant, that is the reason this surface are cool, but this surface are not cool, but the temperature is limit is 306 only. So each and every component I have put it here. This is the component of cooling supply. So the cooling water is or air is temperature rise is maximum is 300 Kelvin. In case of cooling coolant channels, the temperatures are as same as this. So there are I use the modules, a different 3D battery module, and we do the grid independent study. And I supply the mass air with various flow rates, which is 5 degrees centigrade, 5 meter per second to 20 meter per second. And we see the temperatures are at 5 meter per second. If I supply the coolant, the thermal runaway is observed much earlier. In case of 20 meter per second, the thermal runaway is happening at the 350, 300 or 350. And here, so here what I did, here I'm meeting this surface. Intentionally I'm meeting this one, which means this is the default battery. Default battery 4 is the default battery, which means I'm giving the heat. Intentionally I'm giving the heat such that how the temperature is dissipating over the pack and what is the temperature rise. That is what I'm doing. Intentionally I will give the heat, and this is that battery, that the cell temperature. The temperatures are with I supply the various cooling rates 5 to 20. The temperature rises are less, and even though the thermal runaway is happening at 300 seconds at 20 meters per second, in case of 5 meters per second, the thermal runaway is happening and the temperatures are around 1000 degrees centigrade. So from this, we can say that it is cooling. If you supply more cooling, and I can delay the thermal runaway as well as the temperature rise also I am able to control, or the defect battery. So a neighbor cell battery I saw here, I plotted here the neighbor cell 5 and 1 cell. There are thermal runaways happening in the much earlier than the other neighboring cells. Okay, from this we can conclude that so there is a 5 to 20 meters per second, and we observe that after 20 axial airflow which takes place for 20 seconds, the delay the thermal runaway around 161 seconds compared to the 5 meter per second. So now here I'm not giving any, just I'm supplying. I send the air towards to these channels. Then how the temperature behave, how the heat transfer is happening, and I put the one defect battery, which means I had it heated here. I supply heat at 5000 watt per meter square. Then how the behaves whole battery pack. That is what I did here. Now we come to know that the thermal runaways are observed all the mass flow rates, but delay is happening. Now what we did here is we keep the buffel plates. Here is we use cylindrical buffel plate, oval buffels here in the mid various regions. We use, these are the buffel plates we use such that circulation of the airflow is more appropriate, like that we thought, and we understand that we want to see how much I'm able to delay the separation, delay the thermal runaway, as well as how much I'm able to reduce the temperature. So with various flow rates, that is what I did. So we use 3 oval plates, oval buffel modifications, and we see thermal runaway is triggering at 37 seconds. And see here 20 meters per second. So here this one is 5 meters per second. The thermal runaway is happening close to 180 something like that, and 10 meters per second using the buffel plates, oval buffel plates. This thermal runaway is happening around 190 and 5 meters per second. This is what. Now the 3 buffel plates. If I use more buffel plates, the temperature, multiple buffel plates I use, around 10 buffel plates I use. Here I use 3, here is multi, like let's suppose around 8. So this result shows the thermal runaway is happening in all the 3 cases, all the 4 cases. When you see here, the thermal runaway is delayed from because I use multiple Bethel plates in the battery pack. So at 20 meters per second, the thermal runaway is not happening. You see here. So only the mass flow rate 5 meters per second, 10 meters per second, 50 meters per second, the thermal runaway is observed, but temperatures are not so high. And 20 meters per second, up to 800 seconds, the thermal runaway is not happening. Which means even though the temperatures are because of the internal heat resistance and chemical reactions, if I use baffle plates such a way that I can able to minimize or delay the thermal runaway temperature rise, as well as I can eliminate the thermal runaway up to 800 milliseconds, 800 seconds. 800 seconds. That is what we come to know that. So, and again we use triangular baffle plates to improve further. These are the baffle plates I kept here in the battery pack. In the top view you can see here like this. And so when you see here, this is the defected one in the various time scale, how the temperature is dissipating, how the temperatures are happening. So here the defected one I observe here. If it is 10 meters and 5 meters per second, 10 meters per flow rates, the thermal runaway is observed. If 15 and 20, the thermal runaway is not observed up to 800 seconds. So from the conclusions, I can say that we validated single pouch cell and cylindrical cells and localized heating and heating conditions with a different heating power switch, and worst case we observed 500 watt per meter square. If I generate the heat inside the battery, the thermal runaway is not controlled without any cooling. If I air cooling with various baffle plates, I can able to control the heat temperature. We can maintain the temperature within the limit up to certain time, which is as we observed. That the effective one is oval baffle plates are more appropriate to design the cooling system of the battery packs. So these are the references we use for our research, and these are my team. I sincere thanks to my team, which is this work is involved by the Teja and Tejaswini and some Anjana and Abhishek. These 4 are working on this area. So I acknowledge these my students, their sincere efforts and getting good results for this. So I conclude. Thank you so much once again that give me the opportunity to share my research work in this platform. Thank you. If you have any questions, please open for discussion.
Thank you, sir. Participants, you can post your questions in the chat box, or you may unmute and you can raise your questions. Sir, one question from the chat box. How about the sodium ion battery over lithium ion battery towards performance and efficiency?
Frankly, this is a good question, but I am not working on sodium battery, but there are a lot of research is going on the sodium ion batteries. So I'm not knowing exactly how good it is because I'm not working on it area. Maybe there are some more research is going on that. Maybe that would be good. There are use advantage I feel, but I'm not sure exactly how much good it is compared to lithium. Any other questions?
Thank you, sir.
Okay. So I'll sign off there.
Thank you, sir.
Once again. Yeah.
Thank you, sir.
Yes.
Now I invite Dr. P.S.N. Raju, Professor, to give vote of thanks.
Thank you, sir. On behalf of the management, principal, vice principal, and Department of Engineering, we extend our heartfelt gratitude from the speaker, Dr. P. Malkanatha, Associate Professor, Department of Engineering, and IT Legal Services. We have shared his expertise in this civilized sharing platform in this topic, thermal management of lithium ion battery. Sir, the session was incredibly informative. We are grateful to you, sir, for accepting your invitation at short notice. Much thank you for your representation during the session speaker in this FDP. Thank you, sir, once again, on behalf of the organizing team and on my own behalf, I extend my sincere thanks to you, sir. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Tomorrow,
Thank you, Ravi.
we will
Participants, session 2 feedback link is posted in the chat box. It will be active for the next 10 minutes. For the tomorrow's session, day 5, session 1, we have Dr. Shank Abutakir, Associate Professor from PSG College of Technology, Coimbatore, Tamil Nadu, on the topic vibration measurement, methods and their applications. And session 2 by Dr. K. Lingadurai, Professor Mechanical Engineering, Dean, Anna University Regional Campus, Madurai, Tamil Nadu, on the topic 3D surface roughness measurement.
thank you, sir.
Feedback link will be active for the next 10 minutes. Participants, kindly fill up the feedback.